I saw something. You
I'm
had
a
crack
college
me.
graduate as of 2000.
Oh.
Starting salary 45.
I'm sorry.
Okay. Now, I have a little more material on polar coordinates, and then the rest of the time we can use either for homework questions, but there are at least some. Okay. Because if those two things did not take up a whole 50 minutes, then I would just move on to the next thing. But okay. So. So what I have actually is I have two examples. One is just a change of the other, and you can see how even just changing a problem a little bit can also make it substantially more difficult, and hopefully this will leave you better prepared for certain things that might come up on the homework. So look at this integral in terms of Cartesian coordinates, so 0 to 2 in x, and 0 to square root of 2x minus x squared in y. And then, all right. Now, this limit is a bit unfortunate because when you have a situation where the limit is, or it's an expression like square root of 1 minus x squared, or in general, square root of r squared minus x squared, that's easier to deal with because that could be like the y-coordinate of a circle centered at the origin. But we have this x here, and that complicates things. So here's how we can deal with that. A skill you learned long ago, completing the square. Now, this one is easier to handle than the general case because here's something it's something that comes up often enough where it's something that's worth having in your mental cache, if you will, that they have like x plus 1 squared, that is x squared plus 2x plus 1, or x minus 1 squared, x squared minus 2x plus 1. And while you, all of you, if given these, know that it works out to this, or can go ahead and carry it to multiplication, what often comes up is being able to work backwards. If you have something like this, and the ability to recognize, oh, that's a perfect square, can often be useful. Now, the reason why I pointed this out, this one especially, is two of the terms in this one we see up here. So, you can either go through the whole laborious completing the square process on this, or if you have this in mind, you can see, oh, well, all I got to do is if I have minus 1 plus 2x minus x squared, which this is just the negative of this. But since I've thrown in a minus 1, I have to compensate by adding 1. So now you can express this as, so I'll put this term first, then we have minus, and I'll just pull a minus out of all this, x squared minus 2x plus 1. And now we can condense that to a perfect square, 1 minus x minus 1 squared. So, so this is something that is, and this is a y value. So that's important because we now, what we can see is this region that we have in the xy plane. The lower y limit is 0. The upper y limit is described by this equation. And the only reason I would put a y here is because this is one of the limits of my integral with respect to y. Now, if you have something like this that can be troublesome to deal with, and you don't recognize that it's something like this, that's fine. The problem is still doable. What you do in that case is you have to go through a whole process of completing the square on this. And again, so that's something that you've all done at one time or another. I know it's taught in like Math 101. And still arrive at the same conclusion. Now, so what does this describe? I can go ahead and square both sides and do some rearranging. And you get x minus 1 squared plus y squared is equal to 1. Okay. So this describes a circle. But what do we know about the circle? Well, what is there to know about a circle? What are the two aspects that describe a circle completely?
Radius.
Radius and? I hear whispering, but center, yes. My hearing is awful, keep that in mind. Many years of headphones. Okay, so, and loud music blasted through them. So this helps us visualize what we're integrating over. So, region that we have, so we're going from 0 to 2 in x, so we have those boundaries for sure. Actually, I'm going to move that a little closer. Okay. All right, so this is a circle, and we can specify these, or we can read off the equation, the center and the radius. What is the center?
What?
X and y values. Yeah, so x is 1, y is 0. And what's the radius? Yeah. Okay, so it's a shifted unit circle. So here's the center, 1, 0, and whoops. If I put that at the actual midpoint, that would be a lot nicer. Okay. All right, so this is the domain, the two-dimensional domain over which we're integrating. X goes from 0 to 2, y goes from 0 to this curve. So this is y is equal to the square root of 2x minus x squared. So one of the take-home messages, if you will, from this example is when you have something like y is equal to square root of r squared minus x squared, that is dealing with a circle centered at 0, 0, and the radius is equal to r. But if you have something like this, where there's a linear term, so ax minus x squared, so that means that the center is going to be at like a over 2 and 0, and then from a completing a square process, you can figure out the radius. All right. So now polar coordinates are normally best used for circles that are centered at the origin of whatever radius. That's what we saw in the other examples. But having a shifted circle is still not a deal breaker. So the task now that we see this is what the region is, so shade in here. We need to come up with limits in r and theta for evaluating this integral. Because once can anyone tell me, once we convert it to polar coordinates, the limits will be the hard part. The easier part will be the integrand. So what exactly are we going to be integrating in terms of as a function of r and theta? Because we have to convert the integrand to polar coordinates. And we dealt this expression often enough on Monday. yeah, so that is going to become r. Although that is not our integrand. Keep in mind another thing I repeated several times on Monday. What will be missing?
Cosine theta, r cosine theta.
Yeah, we have to throw in that extra factor
R
of r.
squared. Yeah.
So yeah, our integrand will be r squared. So we just need to figure out what the limits are going to be. Now, so we would like inequalities on r and theta. Now, in this case, the easiest one of these to get will be theta, because if you look at this xy plane in terms of quadrants and what angles correspond to what quadrants, as far as in terms of quadrants, where is this region located? At quadrant 1. Not only that, it's going to take up the whole of quadrant 1, because over here we have to go all the way up to here in terms of r.
2.
And even as we move towards this boundary of the quadrant, we still have some pieces of this domain. So we need the whole quadrant. So what angles is first quadrant?
0 to pi over 2.
Yeah, 0 to pi over 2. So those are going to be our limits in theta. We just need to figure out the limits in r.
Are they going to be 0 to 2?
It's not going to be that simple because we're not, you can tell from a picture there are not going to be constant limits in r, and the reason for that is if it was, that would just be a portion of a circle, like a quarter circle, centered at the origin. If you have anything other than a circle centered at the origin, then you're going to have some variable limits in there. Now, how do we get the limits in r? The key is actually written on the board. You use whatever equations define your limits in terms of x and y. So the equation I have written down there, okay, so we have, because, actually I'll shift back for a moment. Okay, look at what's happening for each individual theta. Because you have all this information about the domain from here, but you don't know yet which piece of information is going to help you get the limits. So now that we have our theta limits established, if I start from theta equals 0, I have to go from here all the way to here. So now in that case, r is going from 0 to 2. Then I increase theta, and I go from the origin out to here. You're going in a radial direction because you're trying to find the limits in r. But you find you're going out less and less of a distance until eventually when theta becomes close to pi over 2, you're not going out very far at all. But the reason for this picture, this is why doing this exercise here is important, it tells you which piece of information is pertinent to getting the limit. It's this one, because it's this curve, y is square root of 2x minus x squared, that tells you what your upper r limit is going to be. So once you've identified that, now you can translate that equation to polar coordinates, or equivalently, this equation. This is the one I'll actually work with. Okay. All right, so I'll just repeat it here. So we have x minus 1 squared plus y squared is equal to 1. So now I'll fill in x equals r cosine theta, y equals r sine theta. So we have r cosine theta minus 1 squared plus y squared is equal to 1. So now go ahead and expand all this. So r squared cosine squared theta minus 2r cosine theta plus r squared sine squared theta for y squared is equal to 1. Okay. Oh, what did I forget? What? When I multiply this out, I missed something. Yeah. So this squared minus this time twice this times this plus that squared. So I need that. Then I have r squared sine squared theta is equal to 1. But now the 1s will cancel out. What else can I simplify?
Sine squared theta, cosine squared theta equals 1.
Yeah, so these terms condense to r squared. So now I have r squared minus 2r cosine theta is equal to 0, or I have this. Now, I'm looking for my upper limit in r. So we're dealing with r, because r is starting out at 0, starting out at the origin. But since we care about the upper limit, that's for non-zero r. So I can just divide both sides by r. So this is my upper limit. So now I can write out the integral in polar coordinates. So I evaluate from 0 to pi over 2 in theta, 0 to 2 cosine theta, and then the integrand became r, but there's an extra factor of r, so r squared dr d theta. Okay, now, so now we can go ahead and evaluate this. Now, okay, so first we're going to integrate with respect to r. So what will that give you?
R to the third over 3.
Yeah, r cubed over 3 with limits 0 and 2 cosine theta d theta. And now you go ahead and plug in the limits. So that's just going to give you, we're going to get a 2 cubed or 8. So it's going to be an 8/3 that I can just pull out of the integral. And now we're going to have cosine cubed theta d theta. Now, back in Cal 2, it's covered there, how to handle odd powers of sine and cosine. Does anyone remember how to do that? I know it's kind of a long shot, but... you can, when you have an odd power, that's the easier case, you can set aside 2 of them.
Yeah. Times 1 of them.
And I won't go through the whole thing because this is on page 87 in the notes, but the interesting part I'll go ahead and do. So cosine squared you rewrite as 1 minus sine squared. And then you can do a u substitution. U is equal to sine theta, and then du is cosine theta d theta. So that gives you integral of 1 minus u squared du. And so then you can evaluate that integral and finish it off from there. Okay, so now none of these kind of techniques are necessary, at least for doing it analytically. So any questions? The main thing I want to focus on here was the setup. So, any questions about anything that would happen here? Okay. Now, suppose I change the original integral in x and y just a little bit. The integrand stays the same, but and you'd think a change like this should not affect things very much. Unfortunately, sometimes it does. Okay. So now I change the upper limit in x to 1. Now, let's see how this affects the picture. Everything else I've written on this board, pretty much the same. But now I need to adjust my picture. So I have my same circle as before, center at 1, 0. But now, this is my upper boundary. So it's no longer the whole top half circle. It's just that basically northwest quarter of it. So now we have a little harder time. Now, the theta limit is still going to be 0 to pi over 2. That's not going to change because we still need the whole first quadrant. But this is why I went on about figuring out which part of your boundary determines the upper limit. Because for smaller values of r, it is not the circle that determines your upper limit. It's this line x equals 1. Up to a certain point. And then as you get to larger values of theta, theta going towards pi over 2. So for here, x equals 1 is the boundary. Over here, for larger values of theta, this curve that we had before, 2x minus x squared, determines the upper boundary. So for these larger values of theta, we know what the limit is. So we have r is equal to 2 cosine theta. So what we used for previous example is still useful over here. But now we need to change this equation to polar coordinates. And we still want to limit in terms of r equals something. So if x equals 1 in polar coordinates, it means r cosine theta is equal to 1. So r is going to be 1 over cosine theta, which is also what? What's 1 over cosine? Secant theta. All right, now you can write it either way. I'll just leave it as 1 over cosine for now. So now our limits are going from 0 to either 1 over cosine theta or or 2 cosine theta. So what we still have a result is which is which, and in which case. For which theta do we use either one? So smaller values here use 1 over cosine, larger values use 2 cosine. How are we going to figure out, like algebraically, like not relying on a picture because my pictures are suspect, how can we tell when to switch?
You plug x equals 1 into your y formula to find out where
Yeah,
these
basically,
lines cross.
you see where they intersect. Yeah, because here's the line x equals 1. So at this point, where x equals 1 meets this circle, so in other words, you can just set these two equal to each other. So we switch at 1 over cosine theta is equal to 2 cosine theta. And you can rearrange that to get cosine squared theta is equal to 1/2. Now, so cosine theta is a square root of 2 over 2, or it's also square root of 1/2. So what theta is the tipping point?
45.
Yeah, 45 degrees or pi over 4. So now I can write down what the new integral would be. So this original integral, we have to break it up into 2 because we have 2 limits. So we have integral from 0 to pi over 4 in theta, and then from 0 to this boundary. So 1 over cosine theta, or secant theta, dr, and then we'll have r squared, our same integrand. That's for this first part. And then for the other part, it's from pi over 4 to pi over 2 in theta. And then we go from 0 to 2 cosine theta, r squared dr d theta. Okay. So this is a pretty comprehensive example of, given a description of a region in terms of x and y, how you can get a description of a region in polar coordinates. So more sophisticated examples of what I did on Monday. Okay. Now, if I go ahead and write this as secant theta, and if you were to try to evaluate this integral, it would play out like I did over there. Instead of having cosine cubed theta, you'd now have secant cubed, which is actually a real pain to do. Like integral of secant squared is easy because secant squared is a derivative of tangent. But secant cubed, you'd have integration by parts and so forth. So in fact, when I taught Calc 2 some years ago, I heard from a grapevine that some physics professors here were bragging that they could evaluate integrals better than math professors could. So I gave my students a bonus problem and they couldn't do it. So, and it wasn't secant cubed, it was like secant to the 7th or something like that. So that'll teach them. Okay. Oh, and then what I would give difficult integrals like this to my students as bonus problems. And I've contemplated doing the same thing for you guys because I have some problems that definitely would not be feasible for a test. Especially as we get at triple integrals starting on Friday. However, if I decide to do that sort of thing, I should point out that if you have such an integral to evaluate as a bonus problem and you just go to Wolfram Alpha, Wolfram Alpha and have it do it and show the steps, I know about that trick, so don't even.
Some of our problems take too long to compute. I've tried several problems for a math class, and not math class, physics class, and it didn't work.
Oh.
Even with the pro subscription, it took too long to compute.
Yeah, there's some dastardly ones out there. So, okay, now, do we have any? Okay, well I know we have at least homework questions. You had something or what? Okay. And okay, well, okay. So this is on the homework that was it's coming up due.
No, that was due last night.
Oh, okay, right. We had a homework due last night. 14.1.
You probably did it 2 weeks ago, so.
I can't keep up with like when they do.
Okay, well, we can check on it after class, I guess. Okay. Stuff happens. Which problem was it?
Number 8. This is it.
Oh, okay. Oh, that one. Okay. Yeah, and actually, before I look at that one, since that one was due, the one is coming up due, 14.2. Anyone have questions on those? Okay. You might have one, or
I'm gonna check.
okay, all right. Now, I would encourage you. I am able to make some time on Friday for homework questions, so be sure to bring them. Okay, but now this is still something that's worth doing just because the integrand is a little bit strange. And as far as like the anti-differentiation goes, it's easier than it looks. I'll put it that way. Okay. So this problem is, all right, so integral over rectangle. So the limits are 0 to 5 in x, and then 1 to 2 in y. And the integrand is x over 5 plus xy squared. Okay. Now, because it's a rectangle, you have constant limits for both x and y. I've chosen to have y be the inner integral. And in a lot of cases, it doesn't make a difference in terms of level of difficulty which one you do first. When you have this choice of constant limits for everything, you're perfectly free to do dx or dy as the inner or outer. But in some cases, it significantly does affect the level of difficulty. This is one of those times. Because what you really want to do is, in this case, integrate with respect to y first. Because when you integrate with respect to y, x is considered a constant. So this x, if you had to do this with respect to x, that'd be a real pain. You don't want to do that. But so instead, if you go ahead and pull out the x over here,
Okay.
and then you have,
1 over.
and I'm going to write this as 5 plus xy to the
negative
minus
0.
2. Okay. Now, you're all familiar with the power rule for integration in its simplest form, but I'm going to show you a somewhat more general form. That in general, the integral of ax plus b, where a and b are constants, raised to the nth power, and we're assuming, as usual, that n is not equal to minus 1. So the indefinite integral of that, you'd have ax plus b to the n plus 1 over n plus 1. But then because of a constant of a out here, you have a factor of 1 over a. So really this is the basically the most general form of power rule I can give you. And this is something is good to know because these multiple integrals, especially when triple integrals we get into, can be really tedious. And anything, you might think, oh, I got to multiply this out or something. No, just do this. I think it's a definite time saver, especially on the test, hint, hint. Now, in this case, your constant in front of the y is x. So the indefinite integral of this is going to be 5 plus xy to the minus 1 over minus 1, and then times this factor of 1 over x. And isn't that convenient? Because then these will cancel out. And then you still have the limits of 1 and 2 to plug in for y. Is that the part that was causing difficulty, or? Well, actually, let's go ahead and carry this out one step, a little further. So we plug in limits for 1 and 2 for y. So I have minus 5 plus 2x to the minus 1. Then I have a minus and another minus giving me a plus 5 plus x to the minus 1 dx. So for this, you're not going to use the power rule anymore. You're going to use natural log. So you're going to have two terms involving natural log. So you have minus 1/2 natural log of 5 plus 2x. The 1/2 here is because of the 2 in here. And then you'd have plus natural log of 5 plus x with limits 0 and 5. So any questions about this? All right. Yeah.
Oh, 2. There went the 2. Okay.
This is where it's particularly important to keep in mind how you treat the other variables that are treated as a constant, and that can make a seemingly very difficult problem be easier to tackle.
Why do you have the negative sign in front of that one? Wouldn't it be that minus the next one? Oh, the negative one. Okay.
Okay.
Never mind.
All right. Okay. Are there any other homework questions of any kind? Okay. 13 minutes. Okay. Well, I came prepared for this possibility because I know how you guys are about bringing questions or not. So what I will do is start on triple integrals. And you've seen how tedious the examples could be just for double integrals. So yes, for triple integrals, it does get worse. And then I can continue with triple integrals on Friday, and then whatever homework questions you might have, go ahead and bring those. Okay. Now, for most part, this is just just double integrals for the next level, but it's very similar concepts. You have some region to integrate over, and you come up with limits, but now for x, y, and z. And then later other coordinate systems. And then you integrate with respect to one variable at a time, plugging in these limits. Now, and what we'll see is when the limits are functions of your variables, they can get extremely nasty. So I think the best place to start is with an example. All right, I'm going to describe a solid E, a solid tetrahedron. Okay, and it's bounded by these planes. X equals 0, y equals 0, z equals 0, and x plus y plus z is equal to 1. So the problem here is to evaluate this triple integral over the solid E of this function x times z. And whereas I normally use dA to refer to double integrals, because 2 dimensions you have an element of area, here we have an element of volume, so this is a normal notation dV, used to write general triple integrals. Now, before I get into this, we know that a single integral is area under a curve, and double integral is volume under a surface. What about triple integral? Uses of triple integrals, for instance, they can be used for volume if your integrand is 1. If you're integrating over a three-dimensional solid, it gives you the volume of the solid. If your integrand refers to a density that is not constant, so it varies over the solid, then integrating density over a three-dimensional solid, that's like density times volume, which equals mass. Yeah, so it's a way to compute mass. It can be used for a center mass, certain moments of inertia, things like that. So those are the most common applications of triple integrals. Okay, now it's a good idea to visualize what you're trying to integrate over. So in three-dimensional space, we have now sometimes a tetrahedron can be specified in terms of its vertices also. In this case, we can see that 0, 0, 0 is one of the vertices. It satisfies all three equations, these three equations. But this equation helps identify other vertices. For instance, if x and y are both 0, but z equals 1, that's a vertex. And if x is 1 and the other two are 0, that's a vertex. Or if y equals 1 and x and z are equal to 0, that's a vertex. So we have this plane that's basically out in front with this view that describes the plane. So in front, x plus y plus z is equal to 1. Now, it can also be helpful to view this from a two-dimensional perspective, just looking down on the solid at the xy plane. This can help you figure out your limits in terms of x and y. So we know that x equals 0 is a boundary, y equals 0 is a boundary, and then what about your other boundaries? Well, z equals 0, that is the xy plane. But then you have this. What you could do is, to find out how this boundary impacts the xy plane, you can set z equals 0. And what do you get? You get the equation x plus y is equal to 1. So that's this line right here. So this could be helped. And now, it helps that we know how this tetrahedron behaves from a three-dimensional view, that if we're looking down on solid, like from a positive z-axis, this is what the solid will look like. We're seeing the whole thing. We're not missing anything. And that's important for making sure you have the correct limits. Now, and then this is a point 0, 1, 0, 1, 0, 0, and this is 0, 0, 0. And also the other vertex, 0, 0, 1, it would be sitting here. It's just that these two are in the xy dimensions are superimposed on top of each other. So we can't see them separately. Everywhere else we have z equals 0 because we are in the xy plane. Now, so we can use this to figure out what our limits will be. So the integral of xz dv. So we'll make x, I should not have done that. I didn't want to give that away. That's okay, I'm leaving harder ones for you guys. So I'll make x be my outermost integral, then y, then z, which is the usual ordering, and you want to do that if you can. So x equals 0 is the left boundary, and because of this going out to x is 1, that's why x equals 1 is the upper limit. Now, what about the limits in y? What is the extent of this domain in terms of y? So we have this boundary here and this boundary here. So certainly the lower limit in y would be 0. But what should I fill in for the upper limit in y?
1 minus x.
Yeah, you take this and rearrange it to be y, isolate y. Y equals 1 minus x. Okay. And now if we go back to our overall description here, what should the limits be in z? It's the same idea. You want your lower and upper limits in z.
1 minus x minus y.
Yeah, we take this equation and solve for z. 1 minus x minus y. And then z equals 0 would be the lower limit. So that's it. That's the setup of the integral. Now this is where things get extra ugly. Now, because first we're going to integrate with respect to z. But here I have this x. X is treated as a constant. So I can actually pull it out all the way to here, because it's not going to affect my integral with respect to z or with respect to y. So I can just, it's lying in wait to make things harder later, as if things won't be hard enough already. So now we can integrate with respect to z, and we'll get z squared over 2, plug in limits 0 and 1 minus x minus y, dy then dx. So then, well, of course, that 1/2, that's a constant that we can pull out all the way. And when I plug in this upper limit, plugging in 0, of course, won't give us anything. And we have 0 to x, or 1 minus x. And I have 1 minus x minus y squared dy dx. Okay. Now, this is a perfect example of what I was talking about earlier, using power rule as most general form. if you take this and multiply it out, you're going to have 6 terms altogether, or you might initially have 9 and then you condense them to 6. You're just asking to make a mistake. So don't do that. Don't multiply the whole thing. So we're integrating with respect to y. So this is, so when you anti-differentiate this, you're going to get 1 minus x minus y cubed over 3, and with limits 0 and 1 minus x. And can anyone tell me what I have forgotten?
The x. Should we get a negative?
It's going to be a negative because there's a negative in front of a y. Whatever constant is in front of a y, you must divide by it. So that 1 over a that I had, yeah, it's still there on the board. So I have a minus. Okay. So, what? Okay. Yeah. All right. Oh, there is something. Yeah, I think someone else said that. I had the x down here, and that should still be there. Okay. All right. How are we doing on time? Oh, actually, pretty much out of time. Now, all right. I'll use the last 2 minutes to show how you can make the rest of this easier on yourself. All right. So I have all sorts of shortcuts for these things. Because you might think, okay, now I plug in the limits, and now I have to multiply all that. Okay, so then when you plug in the limits, you get 1/6, integral from 0 to 1, x, 1 minus x cubed dx. So plugging in the 0 and the 1 minus x for y. And right. Now, you might think, oh, now I have to multiply this out. No, you don't. Make a u substitution. Let u equal to 1 minus x. So then du is equal to minus dx. And this is one of those many cases where we're basically putting a shoe on the other foot. Because then what you get as a result of that, and this is worked out on page 89 to 90 in the notes, is you get 1 minus u cubed du with the same limit 0, 1. Because you plug 0, 1 into here, you're going to get 0 and 1 again. So when you have something like this where you have any constant here, do this simple substitution, because now this is trivial to handle the distribution. So then you just have 1/6 u cubed minus u to the 4th du. That can be worked out using a power rule from there. So there's, yeah. So yes, I'm a master at finding ways to get out of having to multiply out things because I just don't want to do it. So you can benefit from my laziness. Okay. Now we'll talk more about triple integrals on Friday, but this is how ugly they can get. Okay. And bring your homework questions on Friday.